So hello everyone, welcome to my presentation on high throughput validation for 400G, 800G optical transceivers. My name is Ali Emsia. I'm a field application engineer in Tektronix based in Germany, Cologne. A brief introduction on the Tektronix. So Tektronix is a leading test and measurements company serving engineers and technical professionals. The company founded in 1946, acquired by Danaher in 2007, and then in 2016, Fortive company acquired Tektronix. The headquarters is in Beaverton, Oregon, US, and we have different key products for different market branches. So we have award winnings in the real-time oscilloscope, sampling oscilloscopes, signal sources such as arbitrary waveform generators, spectrum analyzers, and video tests. So in 2010, we acquired Keithley. So Keithley is a leader in precision electrical tested, which was founded in 1946. The headquarters of the Keithley is in Solon, Ohio. So it offers instruments and systems to meet any measurement requirement from nanovolts to gigahertz. So it also contributed to many awards, as well as honors from the Semiconductor International Solid State Technology and Electronic Products in Test and Measurement World magazines. So Tektronix is a part of Fortive company, as you can see. So the Fortive has more than $6 billion revenue, which is split into professional instrumentation, and under the product realization, you find Tektronix there. And the other branch is industrial technologies with different companies. Here is a brief portfolio of the Tektronix. As you can see, simplifies the serial standards testing complexity with measurements expertise and tools. On the left side, we see our sampling scope and optical clock recovery, which we'll be focusing on in this talk. So next to that, we have the real-time oscilloscope with 70 gigahertz of bandwidth. We have also the optical light wave coherent signal analyzer based on the real-time scope. We are also very active in the real-time spectrum analyzers. On the lower part left, you see the Keithley wafer testing. So it's a characterization of semiconductor at the devices on the wafer level. Also, we see the arbitrary waveform generator from the Tektronix, and finally, we have also a parameter analyzer, curve tracer for LIV characterizations of the optical components on the wafer, such as lasers. So here we see hyperscale data center optical module evolution. So on the left side, you see a traditional spine leaf architecture of the 10 data centers. And on the right side, you see the optical module evolution. You see from the TOR to server, the evolution from year 2012 to 2020. The speed of modules are constantly increasing because of the high bandwidth demand or traffic speed demand as we go further, so the speed gets higher. And this, we start from the TOR to server, which is the top of the rack to the server. For the short reach, we will have different standards. So by year 2022, we will be having 20G active optical cables. Then the second scenario will be the leaf to the top of the rack. We see the modules evolution, which in year 2012 we had QSFP plus. Now we have now 400G QSFP DD. So different standards. So the focus here is data center R4, but we have also the short reach. So basically in the short reach, we talk about the multimode fiber, and it's where we can also have the VCSELs. And as we go higher in the distance, we have also other standards. So from the data center interconnects, so now we are talking about the 400 GZR, which is the coherent based to connect the data centers, because now the data centers future will be the cloud based, which means the data center will be off the premise. It won't be it look like the traditional data centers. And as we go further, then the next generation will be the 800G ZR and OpenZR+. Here is just a small standard interpretation what we are talking about. So if as an example, we have here 400G DR4. So what does it stand for? So 400 shows the data rate. So X here shows the reach. So it stands for the short, which is multimode fiber based, and then D stands for data center. So the category of single mode fiber, as you can see, as the reach gets higher, the category is single mode fiber based. So D stands for data center, F fiber 2 kilometers. When we have here L, it's a long reach 10 kilometer. Then we have extended, and we have the Z, which it stands for coherent 80 kilometers and beyond. And when we have Z plus, then it goes higher than 120 kilometers. And the last alphabets, it shows the number of lanes and wavelengths here. So we talk about 400G data center. R is the scrambled data, and 4 stands for 4 lane. Now, we are facing the live data traffic speed. So what do we need here? Why does the industry need PAM4? So NRZ greater than 28 gigabits per second limits the length and increases the cost. That's why the community defined the PAM4, which we have the 2 bits per symbol. So at 28 gigabaud PAM4, we enable 56 gigabits per second, which needs half the bandwidth. And it allows the designers to develop products to fit cost structures of available channel technologies. So on the right side, you see an example of the theoretical eye diagram of NRZ and PAM4. So the PAM4 eye diagram spans 1 unit interval and consists of a single outer eye with the 3 dependent inner eye diagrams. So which means it has a worse SNR performance. So we have a 3 level. So on the electrical side, the signal to noise ratio is decreased at least by 9.5 dB because of this 3 level. Optical side 4.7. The factor 2 difference between the electrical and optical signaling comes from the converting the SNR electrical voltages to the power. Measurement challenges, what we have as measurement challenges, so it's repeatability of the measurements, stability of the PAM4 signal, which is going to be measured, accuracy, and the speed. These are challenges when someone is manufacturing his transceivers. So let's look at the comparison of PAM4 versus NRZ optical measurements. So on the NRZ measurements, we measure the transmitter eye masks. We measure the optical modulation amplitude and extinction ratio of the transmitter. Now for the PAM measurements, the most important parameter to be measured is transmitter and dispersion eye closure quaternary penalty, TDQ we call it. We have the outer OMA, optical modulation amplitude. We have outer extinction ratio, and we have the level separation mismatch ratio. So these measurements need to be performed to be able to evaluate optical transceivers for 400 GDR and for 800 GDR. So first measurement, as we saw, so the I mask for the NRZ on the right side is a mature measurement, and when we talk about the PAM4, so it's difficult to measure for all these three inner eyes mask for. That's why the standard defined the TDQ for PAM4, which is the measure of each of the optical transmitters' vertical eye closures. So as you can see on the left side, we need to have an algorithm to be able to measure all these vertical openings in the histogram. So here we have two vertical histograms the standard defined, and we need to evaluate all of these 8 crossings of the vertical lines in the eye diagram. So how would we implement these TDQ measurements? You see on the right side 2 pictures. So basically TDQ is the ratio between the ideal simulated PAM4 eye diagram and the received optical eye diagram. So you add up Gaussian noise to your simulated eye diagram to achieve the targeted bit error ratio, which is similar to your measured eye diagram. So the algorithm is as follows. So you see on the first picture an optical PAM4, received PAM4. You have to equalize your signal with the 5 taps feed-forward equalizers defined or recommended by the standards. You determine the thresholds of your eye openings. You optimize the sampling time, and then you have one, as you can see, it is numbered in each eye opening to 6 according to these 2 vertical histograms. You have to find for each of these the vertical eye openings, and they calculate the bit error ratio bathtubs based on the probability distribution function. And then you measure the targeted pair for all of these bathtubs, or you estimate it. And then you measure the TDQ for your optical module. Another measurement is the OMA outer in the case of PAM4, which is different from the NRZ. So it's measured over the central 2 unit intervals of the run of the 7 trees here in the picture you see, and the average optical launch power of the level P0 over the 2 unit intervals of 6 zeros, which means that the standard recommends to have a specific pattern such as PRBS 13Q or SSPRQ. Another important parameter to be measured is extinction ratio on PAM4. As you can see, the difference between the NRZ extinction ratio and PAM4. So you need to also take into account 2 unit intervals on the highest level, P3, and on the lowest level in the case of PAM4 extinction ratio measurements. And here we see RLM, level separation mismatch ratio, defined as a function of the mean signal level transmitted for each PAM4 signal. So on the right side, we see the mismatch between the inner eye diagrams. You can see the middle eye is closed because of this mismatch, because most probably the transmitter is not optimized very well. And on the left side, the eye diagrams, 3 eye diagrams are matched, and the mean value is shown on top of each eye diagram. To be able to evaluate the transmitter correctly, so another challenge is that the standard mandates to use an optical clock recovery in order to guarantee accurate results, unless you prove alternate solution with the same results. So which means that you need to use the optical clock recovery in combination with the optical sampling scope when you are evaluating the transmitter. So this, on the left side, you see a block diagram recommended by the standard. And on the right side, you see the Tektronix optical clock recovery called TCR801.
Adi, sorry to interrupt. Can I ask you to speed it up a bit? We are running out of time.
Yeah, sure. So, and here is a picture of the sampling scope 8 series with the 4 parallel optical inputs and the optical clock recovery. So the most important thing here for the transceiver manufacturers is to reduce the cost during the production. So this sampling scope has a disaggregated software which enables the parallelizations of the analysis based on the cloud or server. In that case, when you are evaluating lots of transceivers, you reduce the costs thereby using this parallelization of the software which is disaggregated. So this slide shows the advantages of the new software on the new sampling scope, which are already mentioned. And these are the measurements which are compatible with the software, which are designed inside the software. All the necessary measurements required by the standard are covered using the software. So another important thing is the scalability of the modules. So you can have either 1 input, 2 inputs, or 4 inputs for parallel measurements on your 4 lanes for 400G DR4, or you can have for 800G, you can have 2 different optical clock recoveries and measure at the same time 8 lanes, which is coming from your module to be manufactured and to be tested. So I'll go to the final slide. So what Tektronix 8 series offer, it first of all, system measurement integrity is a new platform confidence that you can do your measurements and evaluate your transceivers to reduce the cost, especially during the manufacturing, by increasing the speed of the measurements. So core flexibility enables the user to adjust, change the workflow without sending any hardware back to the factory, which means you can receive a higher bandwidth module and mount it yourself. So it gives this flexibility. Another thing is the disaggregated software, which is cloud-based, so you can install the software on different servers or on the cloud and remotely access and do your measurements and acquire the data and send it for offline processing. And last is the simplified single platform. So it's the most compact modular sampling oscilloscope to cover all modes of the tests, PAM4 as well as NRZ. So the software is modern and is optimized for the manufacturing need, and you don't need any complex optioning schemes as a prerequisite to test.